예, 여러분에게 양해를 구한 것처럼 오늘 수업은 제가 부득이한 사정으로 녹화로 좀 대신하겠습니다. Okay, in the last class we learned about the first order linear differential equations, and now we will learn about the other kind of second order differential equations. And here other kind means nonlinear. As we already learned in the first order differential equation, if we have some nonlinear term, if the nonlinear term is involved, then generally the solving the differential equation is much more difficult, and most cases it is impossible. But sometimes it is possible to solve such kind of nonlinear equations. So there are some examples, and we will learn how you can handle such kind of differential equations case by case. Okay, so for example, if we have there are several cases. Case A from A, B, C, D, E, and we will learn case by case. Okay, let's consider the first case. First, the dependent variable y is missing case. Here, if we have a y prime is p, and y double prime is p prime. And sometimes we have encounter such kind of problem, which one has the independent variable x is missing. So y prime is p and y double prime is dp dx. And if we rewrite this one again, then we can write p dp dy. So when we introduce y prime is p, we can make the problem more simpler. For example, for this case, this is the first order differential equation for the p. Okay, so let's take a look more carefully for each case. Okay, so when we have a spring harmonic oscillator problems, the mass of m and the returning force is minus ky, and the damping is proportional to the minus kv, means, or we can say L instead of k, we can write L dy dx. This is velocity. But in many cases, the damping force is proportional not the v, but the proportional v square. So we can handle this kind of problems. Instead of we can replace L dy dt by dy dt square and other coefficient L. So one important problem is, one important thing you have to remember is the dimension of L here and this L is different. Because in first case, L dy dt must be force unit. Because other term is the force unit, so it should be Newton. So in this case, dimension of L must be Newton divided by the velocity. But in this problem, dimension of L is Newton divided by v square. Okay, that's the first thing you have to remember. So even though we express by the same alphabet character L, but the physical meaning of both L are not totally different. And the other thing is, now we have a plus minus sign here. In previous case, we always say plus L dy dt. Because when we write down Newton equation for the direct force or damping force, this is this form and implies the force is acting this minus sign implies force is acting the opposite direction of the velocity. But when we have v square, they are always positive. So they don't have information of the velocity direction. So we set the plus minus sign to make the damping force is acting the opposite direction of the moving direction. There's no damping force acting for the moving direction. That doesn't make sense. So we need this plus minus sign depends on the sign of dy dt. Yeah, here the retarding force opposite of the motion. Okay, so let's think about that. Some special case when t is 0, y is 1, and the mass is 4, and L is 2. So let's think about that. Yeah, here this kind of equation is case of the B, means the x is missing. In this problem, we said that this is t missing. Okay, so this belongs to the case of the independent variable missing case. So let's define the new variable p. Actually, we say this is v, but for the general, we say just p. And we can rewrite the equation in this form. Okay. And using this relation, because we have a dy dt is just p, so we can take the one more derivative, the second derivative dy is corresponding p dp dy. So we have this one. So we can substitute this first, second order and first order differential with this one. So we can write this form. Okay. Or if we divide 4phi in both sides, we have this one. So this is one example of the Bernoulli equation. Okay, for the case of the n is -1. So we can introduce new variable g, which one is corresponding to p square. Then we can using this relation dg dy is corresponding to p square is, g is p square. So we take the derivative with respect to y, we have 2p dp dy. So the equation now, the given equation, we have this form, and this is the first order linear differential equation with respect to the dependent variable g and the independent variable y. So we can solve it. And for this one, by the general solution of the first order linear differential equation, this is corresponding p and q. So we have a I of the exponential dx, and here p is g. Right. So oh, sorry. In this case, we have a p is corresponding. Yeah, p is 1 in this problem because the p is corresponding. So p is 1. So I is c, so it's g. dy p must be plus minus 1. Plus minus 1 y. So this is corresponding plus minus y. So we have a g exponential I or q exponential minus I exponential plus I dy. So q is corresponding minus 1/2 I exponential I is corresponding exponential plus minus y dy. So we have this one. And by the integral by part, we can obtain this one. And g is given by here. And now we initially dy dt is 0 and y is positive. So initially they are rest. So and y is positive. Here. So the initial acceleration is in the negative direction, means now this time t and y, and we said y is starting from the 1. You see the here, and the equilibrium by the this is kind of a spring problem. So they try to accelerate the origin direction. So negative direction. So the particle start from the left, the velocity for small t also this negative direction. So the damping force must be in positive. So we choose the plus sign. So this is the first part, the small t. So from this boundary condition, initial condition, we found the c is this relation, this value. So finally, we can obtain z, which one is corresponding scale of the velocity is this one. So this one is expressed only the function of y, not the t. It's a little bit different form of our previous case. And please keep in mind, this is valid only when dy dt is negative. So the particle initially, starting from the 1, so they are moving to these negative directions. So it depends on the details. They may stop somewhere or they are moving further. So we should check if it will be stop or moving more. So we need some transcendental equations, and it is not easy to solve it. So let's do something more. It is turned out that when it stops, y is negative. So there are something here. And the acting force is distraction. Now, the restoring force, they try to move back to the origin. So they are moving to this direction. That means the drag force, damping force acting in opposite direction. So we have a minus sign. And so on. So we need think about that very carefully. But just imagine that without such details, you can imagine with the damping force, we have such oscillations. But the detail motion is not the simple harmonic oscillator, it's more complicated. But there should be something here. Or sometimes they can do critical damping like behavior. Okay. So next case, if we have a form of y double prime plus fy is zero case. So in that case, actually this case C seems very special, and it's also including the case B. But it is very frequently appeared in physics, so we take a look more carefully this case. Okay, to solve this kind of form, multiply y prime in both sides. So we have this one. And if we take in the integral in both sides, okay, from here to here, yeah, if we taking the okay, for this one, we just think about that. If we taking the derivative of this term, derivative, this one is give us 2 2y prime and dy prime dx. So this is corresponding y double prime. So we cancel out this one. So this one is corresponding to this one by taking the integral. Okay. And this one, y prime means dy dx. So if we taking the integral with respect to x, so this is nothing else this one. Okay. So in the right hand side, integral of 0, so we have a constant. So we have this one. And from here to here means y prime, here the y prime, y double prime means dy prime dx plus fy dy dx. So we can take out dy both sides because it's at 0. So can write in this form. So you can easily obtain this one. So actually you can see this kind of technique many places, many physical equations. So here is some case. And this kind of equation is separable and can be solved. It depends on the details of the integrals, but somehow we can handle it. Because the right-hand side is only function of y, this one, let's say fy, something like that. So this one is again dy dx square. So dy dx is 2 minus f plus minus, and so dy is root plus minus minus f dx. So depends on the details of this integral, it can be solvable. So this is the example of this previous example, this case. Look at this. This is very familiar equation in physics, the Newton equation. And now the right-hand side is force, and the left-hand side mass multiplied by acceleration. And then if we multiply velocity v in both sides, and let's take the integral with respect to time t, then we got this form. Because and this is nothing else but dv dt x v, and we multiplied v in both sides. We have v square, and here this is v, and this one here. If you take the integral, this is half mv square, and this is fx dx. What's the meaning of this one? This equation. As you know, the left-hand side is the kinetic energy. And f dx is corresponding work done by force F. So this equation implies the kinetic energy is nothing. If we consider the initial condition, this is the initial velocity. X0 to x. Okay. So this means the work done by force F is corresponding to the change of the kinetic energy. So that's why in a kinetic energy we have a half by this integral. So in other words, the kinetic energy plus constant energy, this is the potential energy, then they are constant. So this is the energy conservation. So this is the very important equation, and we can use it very frequently in many fields of the physics. So this equation is known as first integral of the differential equation, since we have integrated a second order equation once to get it. Okay, so the next example is case D. If some equation has this form, we have a x square in a second derivative term and x linear term in a first derivative and the constant for the y term. And right hand side we have fx. And this is called Euler or Cauchy equations. And we can change this nonlinear equation to the linear equation by introducing new variable g, which one satisfies this relation. So once we know if you can change this one, you can do it by yourself very easily. But there is some caution, because in this relation we easily found dx, dg by exponential g, but we need dy, dx, and the second derivative of y with respect to g. So let's take the this relation here. So dy dx is dy dg dx. So this equation dx dg is exponential g. So dg dx is exponential minus g. Okay. So this is corresponding minus 1 over x. So this one is dy dg, and here this one is minus x, 1 over minus x. Okay, you may get some idea why we need this thing. Okay, the second derivative, the here is we need to take the derivative with this one with respect to x. So the first one is if we take the derivative with respect to x for this one, we have a second derivative with respect to dg and dg dx. We have multiply this one derivative, so we have a x square 1 over x square. So from this relation, we can obtain x dy dx is minus dy dg. And from here, this one is also minus s square. So this one is x square here plus dy dg. We have a minus sign here. There's some missing in the sign. Yeah, it should be minus. I missed something. Anyway, so we can obtain this relation. You can check it. So with this relation, we can substitute this one to here, because we have a y x dy dx, and x square dy dx. This one we can replace by this one. So we can rewrite this equation. And this is first order and the second order linear differential equation. So you can easily solve it. But the function f now function of exponential g. Okay, so there is some idea you can handle such kind of problems, and we call this is Euler or Cauchy equations. So the key idea is how you can find some kind of such relation. That's the key idea. If you know this one, you can somehow handle it. But without such idea, it is very difficult to find the proper solution for the given differential equations. But as I mentioned several times, nowadays you don't need to worry about that. You can use computer software. You can easily solve such equations. Okay, so the case E is we can reduce the order of the differential equation. So if we have a dysfunctional form, here the coefficient is function of x, in generally the functional form. And if we have one solution, ux, then the second solution may be the multiplication of a new function of the v, which one is multiplied by u and v. And let's substitute this one to here. So in that case, you can substitute to here. Y prime is u prime v plus u v. Sorry, u v prime, and y double prime y double prime 펜이 자꾸 이상하네요. 뭐지? 자, y 더블 프라임은 u 더블 프라임 v 플러스 2u 프라임 v 프라임 플러스 u v 더블 프라임. 이걸 여기다 넣어주면은 어떻게 되느냐? u 더블 프라임 자, v에 대해서 한번 모아봅시다. v에 대해서 모아보면은 u v 더블 프라임 플러스 u 프라임 v 프라임 플러스 u 플러스 v. 그래서 요걸 넣어주면은 fx u 프라임 v 플러스 fx uv 프라임 플러스 g의 uv가 돼요. Okay. This one is uv prime plus 2u prime plus x u v prime plus u double prime plus fx u prime plus g s u의 v. 자, 이게 this is equal must be zero. So the coefficient of Vx is this one. Now we assume the u is a solution of this original equation, so this must be 0. So now we have a v double prime plus 2u prime plus fx u v prime is 0. So now if we introduce w by v prime, then this is v prime plus w. Now we have a first order differential equation, and it is separable. So somehow you can handle it. This is the idea. Okay, we learned some example of some special case of the second order differential equation. And in this section, we will learn about the Laplace transform. We already learned about the general form of the integral transform, and the first example was Fourier transform. And Fourier transform is very powerful and very useful in many fields of the physics. And also the Laplace transform is also very useful in many engineering problems, especially circuit problems. So, thoroughly the electronics and 전기전자과죠. 여기서는 Laplace transform is more popular compared to the Laplace, the Fourier transform, especially for the circuit peoples. Okay, so let's think about what is the Laplace transform. Very similar to the Fourier transform, we have a such kernel, but now we have a real exponential minus pt, not the complex number, and the integral range is only from 0 to infinite. So we say this is Laplace transform of function f, function of the time, and the obtained result is function of p, and we use the capital F for the transformed function. So this is, as I said, one of the example of the integral transform. And we already learned the Fourier transform, and we will learn Hilbert transform if we have time. And depends on this function, this integral can be easily solved. So let's take some example. For the given f here, very useful functions which we usually using in many cases. There are so many examples. And we have a Laplace transform result fp, or in other words, let's say y. Then we have this relation. We can easily check it. It's correct. Usually that kind of integral is not so difficult. We have such number. And here, more numbers. And you will go on using this table sometimes. It's very important. And as I said, this Laplace transform is very important in a circuit analysis. So such kind of pulse function or such kind of square function will be very useful to remember. And yeah, okay, we'll see how we can use it. And don't worry, I don't want to ask you to remember all these kind of integrals. If you need it, you can do it by yourself. Okay. Also, there is something more. If we have some function g, which one is function of at, not the t, then we have this relation, and so on. So we have such relation and so on. We have some convolution that is important. We will learn it. And also transform of derivative, which one is very important. So please pay your attention for these two cases. So sometimes I'm using this number, but sometimes using we can derive directly. Okay, so let's try to prove some of them. So L1. So L1 is corresponding, Ft is just 1, the constant case. So we have a Ft here and exponential minus Pt. And this exponential integral, we have this one, and we have a 1 over P. But here we assume P is positive because this one will be disappeared at the infinite. And if P is complex, then real part P must be positive. Otherwise, they are diverging. So if you look at this table, there's some limitation for each of them. Okay. And let's think about L2. L2 is corresponding exponential minus AT. So Laplace transform, we have this form. And the result is P plus A, and the real part of P plus A must be positive to guarantee the convergence. And if we multiply the constant C, then we obtain the multiplied constant C to the result of the Laplace transform. And sum of two functions, we have a sum of two Laplace transform. So in this idea, we can say Laplace transform satisfies the linear condition. So the L, now L is the linear operator in a Laplace transform. And we can verify L3, and we can replace A by exponential minus IA. Okay, Ft is exponential IA t. Then this one is written by exponential AT plus I sine AT. Here, this A, this minus A must be replaced by I omega, IA. So we have this relation. And once we offset this one, as Laplace transform of exponential minus AT is, we already know P plus A, 1 over P plus A. And so if we have a IAT, P minus IA, this one. And this one. And P minus IA, the real part of P minus 1 minus A must be positive. And let's compare to both sides. The Laplace transform of cosine A plus I sine AT, this is exponential IAT. They must be same to this one. This one is here. And let's compare the real part and the imaginary part each other. So we can say cosine AT is this one, the sine AT is this one. And if we have minus here, we have this one. So now we just prove this one. Okay. And this one implies this one is actually same meaning of this one, because the P plus IA, the real part of it, this is corresponding real part of P plus imaginary part minus imaginary part of A. So in case we taking this condition. Okay. And we want qualified L11 starting from L4. The 11 is this one, T 곱하기 T multiply sin AT. So now we have a the Laplace transform of cosine AT as this form. And let's take the derivative in both sides with respect to A. Here, in both sides. This one, we have a minus T sin AT. And this one, when you take the derivative with respect to A, we have this one. So now, Fourier transform of T sin AT as this one. This is corresponding L11. And so on. So you can prove all these tables. And why the Laplace transform is useful? Let's think about that. Using Laplace transform to solve the differential equation. Okay, so let's find the Laplace transform of L prime or Y prime here, corresponding to this one. So actually, if you consider the second derivative, second order differential equation, you need relation only this one. If you consider the nth order differential equation, you need to pay attention this relation. But it looks very complicated, but the relation is not so complicated. You can easily find the rule. Okay, so here is the Laplace transform of Y prime. And by multiply exponential minus pt, you can take the part integral by part. So we can take the integral for the first part. So we have a yt. And the integral, we have a yt multiply the derivative of exponential minus pt. So we have an extra minus p here. So you can rewrite this one in this form here. Here, this one is corresponding at the infinite, this term go to 0, and yt is not, if yt is not divergent at the infinite, they must be disappeared. And when t is 0, this is corresponding, this is 1, this is just 1, and this is y0. Yeah. And the minus sign is came from, this is this term. And we have a 2 minus, so we have plus. And this is nothing else, Ly. Right? So we have this relation. Py, the L small y is capital Y. So we have this relation. Which one is corresponding to this one. And this y0 is corresponding the initial value of the y. And let's do same thing for the y double prime. And instead of the y double prime, we just imagine this is nothing else, the u prime. Here u is y prime. So we have a this one is corresponding large u p large u minus u0. And this is because u is y prime, so capital U is corresponding P y minus y0. This is corresponding y0. Sorry, this is P y y0. This is u0, small u0 is corresponding this one, and this is y prime because u is y prime. So now we have a p y square and p y0 and y prime 0. So here is key idea. Now the second derivative is changing to the p square, while the first derivative we have a p. So look at this relation. The third derivative we have a cube of p and p square and p. And nth derivative we have a pn minus 1 and so on. And if set this y, the remaining part, it only depends on the initial condition. So the Laplace transform, we can change the differential equation to the usual equation for the polynomial equation for the p. Okay. So this is the idea how you can apply Laplace transform to solve the differential equation. So the differential equation change to the polynomial equations. Here is example. If we have such differential equation, which one is we can easily solve by the kind of a harmonic oscillator, and the right hand side we have some particular solution. And if we have such initial condition, then let's take the Laplace transform in both sides. So this is Laplace transform of y double prime, and this one is corresponding Laplace transform of y prime, and this is y. And the right hand side, we have this relation. Now we are using L35 and L6. Yeah. L6 is corresponding to this one. And L35 means this one, and L6 corresponding, let's see here, this one, exponential tk, exponential minus at. So now k is corresponding to 2, and a is 2. So we have this relation. Actually, you can do it by yourself. Okay, so we have an initial condition of this one. So in Laplace transform, if we have this kind of zero initial condition, problem is getting much easier because all this term will be disappeared. So now we have only this one in the left-hand side and the right-hand side here. And we can say this one is nothing else square of the p plus 2, so can divide by p plus 2 square. We have this relation. And this one is the Laplace transform of solution which we want to find. So the remaining problem is take the inverse Laplace transform. And if you take a look the table, you can find this one is corresponding to by the L6. You can find this one, or you can write down this one. So you can easily imagine if we have a right hand side in this form, and look at this. This one is p plus 2 cube. So we have a double root case. So we need some special treatment. But with this Laplace equation, you can easily obtain this solution. So if we getting familiar with the Laplace transform for some special purpose, you can easily you can find the inverse Laplace transform of this relation very easily. Okay, so let's take one more example. Y double prime plus 4 y is sine 2t. And we have this initial condition. And let's take the Laplace transform. This is a second derivative, and this is the small y. And if we take the Laplace transform of sine 2t, we have this one. And by this initial condition, we have this form, and finally can obtain the capital Y is this form. And if we take in the inverse transform by the table, the small y must be, this one is corresponding to here, this one is corresponding to here, and this form. Okay. So from typical method to solve the differential equation here, you can easily find the homogeneous solution or complementary solution must be sine 2t plus that. And so this is corresponding to this part. And this one is from the particular solution because we have a double root, equal root. So we multiply 1t here, but to find this one, we need some trick. But for the Laplace transform, it's very straightforward. You can do it directly. If you once know this table. That's the benefit. And let's take one more example here. And this initial condition. And take the Laplace transform, the double second derivative, the first derivative here, and this one here. And Laplace transform of this one is here. And then now the problem is finding the capital Y is algebra equations, and it looks very ugly, but somehow we can handle it. But the problem is, what's the inverse Laplace transform of this complicated function? The key idea is you can divide this by part. So we can separate several things, something like this. Then you can obtain this form. Okay. And you can easily check this one. The complementary solution of this one is in this case alpha, root of alpha must be -2 plus minus 4. Okay, so we will 9 Sine. So this is the corresponding to here, and this one is corresponding 3t things. Okay. But compared to this one, if you are using the table, this is sometimes much easier. Okay, now if we have two equations, the set of equations in this form, they are y and mixed of y and z with the initial condition. So let's introduce Laplace transform for the g and y. So we have a capital G, capital Y. And if you take the Laplace equation, we have this form. And if you rearrange this one with the initial condition, this is nothing else, just a simultaneous equation for the capital Y and capital G. So you can obtain the capital Y and G as a function of P, and taking the inverse Fourier transform, you can obtain the solution. And here we can find the G, because here we can replace G. G is minus y prime plus 2y. So we can substitute G to here. Then, here we have this relation. Either way, it depends on the details of the problems. Okay, I think it's time to finish today's lecture. I'm really sorry about the recorded lecture for this time, and see you in Wednesday.